for giving me the opportunity to present some of our activities within the project MAPP. So I will try to find a good place to stand. So several of you that are in the audience have already seen some of these activities in this project. I will be showing some background, some preliminary results, some work in progress, because even though Stelios has mentioned that the project will finish in 3 weeks, you will see there are many activities where we have results which are, as we call them, work in progress, because we don't quite understand the results. So I can use this, I think. So the project is called Metrology for Aerosol Optical Properties. So it's not only aerosol optical depth, but it's also uncertainties and metrology on the inversion products that you get when you invert the measurements from the ground-based instruments to retrieve aerosol properties. The aim of the project, which started about 3 years ago, is to develop methods and devices for providing traceability. I will briefly introduce the term metrology and traceability on the next slide. We would like to derive and validate top-of-the-atmosphere solar spectra, because this is critical when you are trying to retrieve atmospheric products from remote sensing instruments that are measuring from the ground. And of course, when you talk about metrology and traceability, then you need also to put uncertainty bounds on your measurements. And so also the development of uncertainty budgets and uncertainties was also a major topic of this project. So why do we care about traceability? This is a statement that I took out of the VIM, which is the International Vocabulary for Metrology. And there it says that when you take a measurement, then essentially your measurement has to be traceable, and traceable means that you have an unbroken chain of calibrations that goes back to whatever primary standard you are using for that measurement. So as a simple example, if you are having a watch with a second and you're measuring the time, then basically you are trying to calibrate that clock with respect to your time server, and the time server is traceable finally to an atomic clock somewhere in a metrology center. And so that would be an unbroken chain of calibrations. And in our case, we are measuring radiation, and so we have a traceability to different primary standards. But the idea is still the same. You can go back to a recognized primary standard. And the measurement without uncertainty is meaningless, because then you don't know how much you can trust it. You need that kind of comparability between measurements. So if you have a network and you have different stations located far away, the only way to be able to compare measurements from these different stations is if they have been calibrated to a common reference. And so that brings again the term of traceability and calibration. And recognized unit for measurements is the International System of Units, abbreviated with SI, as you all know. So what are we talking about in the project and in my presentation? It's instruments that are used to measure aerosol properties, passive remote sensing, so it's not a LiDAR, it's not an active instrument, it's really just receiving radiation from the sun or the moon. And from that data, we are trying to retrieve aerosol properties. And the instruments that were investigated in this project were the standard sun photometers that all of you are involved in, CMELS, I will use this nice pointer, CMELS, the Près des Pommes from the Skynet, the PFR, the precision filter radiometers that we are actually building here in the Institute, and Natalia might be showing you some of them during the tour this afternoon. And what we have called emerging technology, which is not so emerging in fact, but maybe the application of these instruments is emerging, is the use of spectroradiometers for retrieving also these atmospheric parameters, trace gases, aerosols, etc. And the properties of the aerosols that we have been investigating are Mainly, of course, the aerosol optical depth, because this is the main characteristic that you need when you are trying to understand climate change, but of course also the other parameters that you can obtain from inverting these measurements, like single scatter albedo, size distributions, and so on. So the project was really trying to provide SI traceable methods towards these measurements. So the implication was that this doesn't exist so far. So we have tried to elaborate different techniques, devices, calibration measurements, and developments in order to try to provide SI traceability to the networks that are in operation and also to new developments like these spectroradiometers. And to highlight the change that we would like to introduce eventually, so not at the end of the project clearly, but maybe in the near to long-term future, is to go away, if we can, from the current calibration scheme that is in use in most of the networks. I should say Skynet is a different one, but for Aeronet and, for example, for our network, this is the standard operation that you are hosting a main primary calibration site. The calibration instruments themselves are being calibrated at remote sites. High altitudes are necessary for that calibration, and so they need to travel back and forth, in our case to Mauna Loa, to Izania on the Canary Islands. They come back, and here they will form what we are calling the triad reference. And our network instruments that are also scattered all over the world, here, for example, in China or in Greenland, they will come and visit us about 1 to 2 times per 2 or 3 years. They get compared to this WMO PFR triad, and that is how we are trying to harmonize our network. And you can see that it's quite logistically quite complex and requires quite a lot of manpower and logistics to operate. And so that was one of the aims to try to improve on this, let's say, quite complex calibration scheme. The reason also why this is maybe a bit of a delicate calibration procedure is that when something goes wrong, like happened this year in December, as we all know, the volcano exploded in Mauna Loa. There started to be lava flows over the roads, and the site was actually closed after a couple of weeks here of these lava flows, and the site has lost power. It's been inoperative for the last couple of months. And so the whole network operation of Aeronet has been halted, and they have had to find different sites for the calibration. So you can see that actually relying on this type of complex calibration scheme can have also its caveats and its problems. So maybe one reason more why we would like to be able to offer a different approach, more simple, maybe only based on laboratory calibrations, so that you are not being affected by natural events like that. So enough of motivation. Let's get to some results. So the calibration scheme currently, and here I use the Aeronet example, is quite complex. And so I will just walk you through briefly through this slide, because there will be quite a few coming up afterwards. And so we have 2 slides here. One part describes the calibration scheme, how to obtain aerosol optical depth from direct irradiance measurements. These instruments look at the sun and can retrieve then the atmospheric absorption and then calculate how much of that is due to the aerosols. And then, as you know, this instrument looks around the sky, makes radiance measurements, and these radiance measurements follow a different calibration route. These, in fact, they are actually calibrated in the laboratory with a calibration scheme that is based on an integrating sphere that is being, in fact, calibrated relative to SI units. And so I actually put this in yellow to just demonstrate that this is actually an SI traceable measurement, while this one here is actually completely untraceable in the sense of going back to primary standards that are based in metrology labs. And so the first activity that we tried to do is to try to see if we could change the calibration mechanism here. And as pointed out here, AUD is a transmission measurement of the atmosphere. So we are sitting on the ground, we are looking at the sun or the moon. That's something that has come up recently. And so you look at the transmission of the atmosphere, which means you need to know what is on the top before it actually gets absorbed. And so the usual procedure is you can do that using Langley plots on high mountain stations. And so our idea was, how could we replace that? And we did that here. We got rid of this Langley calibration. And we replaced it here with a laboratory calibration. So we, instead of going to a high mountain station, we go into lab, we go in our basement, we do the calibration there. And so actually the irradiances that this instrument measures are now in SI units, watt per square meter per nanometer if you have a spectroradiometer. And so what we need is this top of the atmosphere, which nowadays you can get from satellites. And so our approach was to use solar spectrum that you can get from the literature, from satellite-based measurements. So they are completely independent. The instrument and the solar spectrum are completely independent. You bring them, these things together, and then you can also calculate the aerosol optical depth. So we did that. And first, we did that with one of our instruments, which is the PFR, Precision Filter Radiometer. It is work that we started quite a few years ago, even before we started with the project. And during the project, we could extend the work that we did, and it was mainly Natalia that was responsible for that. And so we actually brought this instrument to this really nice facility at the German Metrology Institute. It's in a huge clean room. It's based on tunable laser sources where you can actually measure the instrument responsivity versus wavelength. So you get the transmission of the instrument for all the channels at which it's measuring. And then using that information, your ground-based measurements become traceable to SI. We took a top of the atmosphere solar spectrum, and we then used that to calculate the aerosol optical depth, and we compared that to the standard approach, where the same instrument was actually brought up to one of these mountain stations, and we compared the results, which are shown down here. And we used different types of solar spectra. We used one that we developed ourselves called Quasumi FTS. We used a very old one called Atlas that was based on measurements from the 90s. And we used one very recent one that was just published, I think 3 years ago, from an experiment called Thesis. And so down here you see the results in terms of optical depth difference to the standard approach. And you can see here in light blue the boundaries of about 0.01 in optical depth, corresponding more or less to 1% uncertainty in the radiation measurements. And you can see that these highlighted dots here are all within less than 0.5%. So the procedure worked really well with our PFR instrument. And so we were quite hopeful that we could extend that work on additional instruments from other networks, like from the CML or from the Skynet. Now, as you have heard at the beginning, we did also work on these emergent technologies called spectroradiometers. So we did the same very recently, actually last September in Isania. We had a really nice campaign. We stayed there for about 3 weeks. Very good conditions to actually make this type of measurements. And you see here an example from one of our instruments that it's actually a combined instrument that measures from the UV continuously all the way up to about 2.1 microns. You can see here the measurements during 1 day. So clearly the solar spectrum changes. And in black, I have put in here the top of the atmosphere solar spectrum from this Thesis one that we have selected as our reference. And so this difference between these measurements from the ground to the one that is on top of the atmosphere is actually what the atmosphere is absorbing. And so that is what we are actually trying to quantify. The first exercise that we did is that we used the Langley plot technique as well, because we were at this high mountain station, to see how much we could actually approximate and validate the solar spectrum. And you see here on the top graph, you see actually this extrapolated solar spectra. Here I have shown extrapolations from 2 of our instruments, the Quasumi, that is a double monochromator scanning spectroradiometer. We have extended its range from 500 nanometers all the way up to 1.7 microns, and the BTS instruments developed by Gigahertz, which have given us the data to provide this extrapolated solar spectra. And what you first can see is that in these regions where there's really high atmospheric absorption, actually quite saturated absorption, this extrapolation doesn't work anymore. And that's a problem when you are sitting on the ground and you want to retrieve the top of the atmosphere. Then in these regions, you cannot do that. So the Langley plot actually doesn't work in that region, as you can see. In the other regions, it works quite well. And down here, you actually see the ratio between this satellite ratio spectra and the measurements that we did from the ground with our own calibrations based on these laboratory calibrations. And to cut the story short, I put in here this 1% gray bar. You can see it better without this pointer. And you can see there are two colors because there's the BTS and there's the Quasumé. We have some more colors in the UV, but I wouldn't mention that too much. You can look at the red one as an example. And you can see we actually are within 1%. So you can see that there's quite a high consistency between the ground-based calibrations and the satellite-based calibration. And that is what is actually required if you want then to retrieve the atmospheric absorption, which is just the ratio between the top of the atmosphere and your ground-based measurements. So based on these measurements, we had high expectations that we can actually retrieve the aerosol optical depth from these measurements. And so we did that, of course, with the same data that you have already seen, but the retrieval was based on the satellite solar spectrum. And this is just an example for one day, one measurement, the spectral aerosol optical depth from 300 nanometers up to 2.15 microns. It's a combination of different instruments. We have the Quasumé instruments, we have the BTS systems, we have our own PSR, precision solar spectroradiometer, and we put in also the channels of the standard instruments like the CMEL and the PFR. And on this plot, you can see that the aerosol optical depth is very low. And in addition, there's a very high agreement in these unsaturated spectral bands with these different instruments. And I have another figure that shows actually the diurnal variation on these spectral bands where the CMEL and the PFR have data. And you can see here the same instruments, but now shown over time. Here you have the time. It's for the 13th of September in Isania. And you see the different instruments. You see also the CMEL and the PFR that have the Langley-based standard calibration of their networks. And you can see there's actually quite a good agreement between the instruments, and I put in these gray bars here because they represent the expectations that we have when we measure aerosol optical depth. This is what is called this WMO criteria that tell us that when instruments measure to within this gray area, then everything is fine, instruments are consistent, and the data is of high quality. And so this is for one day, but we have data for more days, and the agreement was very similar to that. So the conclusion was that with these spectroradiometers, with this methodology, things have been working really well in trying to retrieve this aerosol optical depth from these SI traceable measurements. Coming back to this scheme, there's the possibility that we can combine some of these calibrations and we can get rid of this sphere calibration, for example, and just rely on this primary lab calibration and somehow bring the irradiance calibration and the radiance calibration together. The information that we need for that is the field of view of the instrument. Basically, it's a solid angle. Then the conversion is actually very trivial. You see, it's really just a multiplication. From one calibration to the other, you can just swap between the two calibrations if you know your solid angle of the instrument. And so you can actually rely on a single calibration with a characterization of your instrument to try to also retrieve your aerosol properties. Similarly, you can get rid of the laboratory calibration of your direct irradiance, and you can just rely on your sphere calibration. It's just a matter of what you prefer, of where you think you get the lower uncertainties. So you have these different possibilities. And what we did is we played around with these different schemes to see how well one of them would work, how consistent they would be. And this is actually the work in progress. So we did that. We actually did it over the course of the project. We did it with 3 CMLs. We also did it with some Pré POMs, but I'm not showing the results from them on this slide. This is really just CML sun photometers that we tested. And this is a complicated slide. So let me just show you briefly what we have seen. So if we compare the radiance calibration between what we have done, what is the MAPP, with the Aeronet calibration that is based on the Aeronet-based calibration, then the gray bars again represent roughly where we would like to be. Within, let's say, 2%, everyone would be happy. We are not exactly there. Nearly, but not all the time. There are some wavelengths, some channels that are outside. There are some channels that are inside. There are some spectral behavior that we don't understand. So this is something where we still don't quite know where we are. We have not really placed uncertainty bars, as you can see, yet on these dots, so we are not yet finished with this analysis. The middle one is actually the more interesting one, because this one is the irradiance ratio. So this is the one that we use to retrieve the aerosol optical depth. And this is highlighted here by saying that what we compare is the laboratory calibration with the Langley plot calibration, where I have just shown you before that with the spectroradiometer, it works extremely well. With the PFR, it works extremely well. With the CML, it doesn't work so well, unfortunately. You can see that we have quite some discrepancies between these 2 types of calibrations, and we are quite puzzled where that comes from. And the last one, I will come to that. No, I have removed the slide. So this is actually the only slide where we actually show the cross correlation, the cross consistency between these calibrations. So when we have this radiance calibration and when we have the irradiance calibration, then as I showed you, you can move between the 2 calibrations based on your solid angle. And we have the solid angle of all of these instruments measured in our laboratory. And so we can actually compare all these 3 calibrations with the solid angle of our laboratory. And you can see that ideally you would like to be again in the middle. And you can see that our laboratory calibrations in red actually are not that consistent. The blue calibrations that are based on the Aeronet calibration with Langley plot and their sphere, it's also not that consistent. And I should say that down here, this one, it's actually a plot that we just made up this morning. So it's really the most recent data. It was measured at the PTB this morning. And you can see here the red dots. That's really very recent, work in progress, as I said. And we are puzzled why there's a 2% offset. So we believe that our measurements have much lower uncertainty than this 2%. So this is something that we are also trying to understand better. That brings me nearly to the end. So what have we done? We have tried out different traceability routes. This is now focused more on what we have done for the CML instruments. We have the possibility of going through that route, irradiance calibration, knowing the solid angle and the top of the atmosphere spectrum, you can get to your aerosol properties. You can do the same via irradiance calibration. You could go this route, which I have not really mentioned, but it's fairly obvious. You could also do a Langley calibration, and knowing the top of the atmosphere solar spectrum, you could actually calibrate your instrument. And I put here only some dotted lines because so far there's no traceable solar spectrum in space, because as soon as you launch your rocket, then the measurement and the satellite on top of the rocket is not traceable anymore. So you so far don't have traceable solar spectra in space. This is something that in the future hopefully will change. So yes, these were our different schemes. You have seen the results. Some of them are excellent. Some of them are still a bit puzzling. And so this brings me simply to my conclusion that we are able to provide laboratory-based calibrations, but not with all instrument types, interestingly enough. The top of the atmosphere solar spectrum thesis is excellent for this type of work. So before that solar spectrum, our main problem was actually to know what is on the top of the atmosphere. Now we actually believe that this solar spectrum, publicly available on the website, you can download it. You will have it to within better than 1%. And the consistency that I just mentioned, as you can see, it's still work in progress. So thank you very much for your attention, and 2 minutes for questions.
Thank you, Julian, very much. We have some time for questions, if you have on this presentation. Alkis?
Julian, how do you deal with the slopes in the shape of your field of view of the instrument? When you put the limit.
So we have measurements that extend to a certain range, and fortunately enough, the field of view of these instruments that we have been looking at with the collimation tube, when the field of view goes past about 1.5 degrees, then the rejection is about a factor of 1,000. So we have only a promille left. And when we do the integral of this field of view to get the solid angle, then what we are missing is of the order of a few promille, a few tenths of a percent. And so that is basically where we limit ourselves to this 1.5 degree scan. And then we calculate from that integral the solid angle.
Carlos?
Yes. And do you know what is the dynamic range of your irradiance calibration with the tunable laser and so on?
Yes. So I don't know how slow this is going back. I will just show it, even though you don't really see it, but it's still helpful. Here, this is, of course, shown on a linear scale. When you move that into the logarithmic scale, then these tunable laser sources that we have access to, and actually, Natalia will show you one that we have in the basement, so we also have our own tunable laser. They are so powerful that you can measure this instrument responsivity to about 10 to the minus 5. And so we actually have measured the instrument responsivities of the sun photometers over the whole range. So not only around their center wavelength, but all the way from the UV to the far infrared, in order to see if there's also some maybe transmission in other areas of the filters. And so all that data has been actually measured during this project for a sample of instruments. So for 3 CMLs, for 2 Près des Pommes, for several PFRs, and all of this data is actually available for the analysis for this type of questions.
Okay, any more questions? No? Okay, thank you very much, Julian. Just a comment that it's this project is a try to link, let's say, the traditional Langley calibrations and the instrument comparisons with something related or traceable to SI. So it's probably a start of linking all this traditional calibration to something new. And